Okay, perfect. So lecture 24. It is, and that's a 4. Perfect. So we talked about the semi-flexible polymer models last week, and started with the discrete description, the Kroski-Korod model, to then take the continuum limit and arrive at the worm-like chain. And today I want to continue on the continuous worm-like chain model, and then also introduce the weakly bending rod approximation that actually allows us to solve the statistics of these semi-flexible polymers. So to arrive at the continuous worm-like chain description, we take the continuum limit sending b to 0 and to infinity, with setting the length of the polymer fixed, and also the interaction between subsequent joints to stay a finite quantity. This mapping then allows us to identify the persistence lengths as B times K, the interaction strength, or the normalized interaction strength, J over KBT. And B, remember, was the Kuhn length, as a segment length L over N. So that's then, if we use this nomenclature, we can here identify a J over N that gives our finite epsilon. And what's left is an L KBT epsilon. And this L times epsilon I identify now as kappa KBT. So here this kappa, we're going to use this as a continuous bending stiffness, is defined as a epsilon times L, which if we is equal to the definition of the persistence length KBT, if we use this mapping. I'm going to come back to that. That's the bending stiffness. Note that the way we're taking here now, the continuum limit is different for the flexible polymers, because we're keeping the end-to-end, not the end-to-end distance B squared N fixed, which was the case for flexible polymer, but the total length of the polymer. Why is that? Well, because we, as an intrinsic parameter of the limiting cases of there are two limiting cases of the worm-like chain: the Gaussian chain for very flexible, semi-flexible polymers, and the rod for very stiff semi-flexible polymers. And this is basically considering as a reference the intrinsic length scale of the rod. So note the limit here differs from the Gaussian. Chain limit, where we had R squared and B squared finite fixed. Whereas here I have LBN and LB as B beta kappa fixed. So in the continuum limit, we go from sums over segments. These become integrals over the arc length of the polymer stretching from 0 to L. So that's a contour integral over arc length S, which we can map from the discretized version as I times B, I being the index of subsequent segments and B the segment lengths, which we set to 0. Then the, remember the bending stiffness was the deviation and angle from the straight rod limit, which we can write as 1, the rod limit, and here the deviations is the scalar product of 2 subsequent tangents, which, given that they're normalized to 1 each, this is just proportional to the angle they enclose. And this I can also write as a half Ti minus Ti plus, oh sorry, Ti plus 1 minus Ti squared, because the square of the tangents, they give a 1 each, divided by 2 gives the 1, and then the cross term gives minus 2 and the product of the tangents. And now this formulation, if we take the continuum limit, becomes a half b squared for the normal, well, the length of the tangents, and this is then the contour derivative of the tangent parameterized by the arc length squared. This has a physical meaning. This, for a curve in space, is the inverse of the squared of the local curvature. So this is R C for curvature minus square minus 2 square of local curvature. And then our Hamiltonian that depends on the position of our curve in space is a half, kappa half, 0 to L ds dt SDS squared. And the tangent we can also write as obviously the derivative of the space curve. So that's then equivalent to also writing d squared r of s ds squared to half 2. So this is now a functional of the polymer contour. And so the only thing that we need to consider when now taking this continuum limit is that all the time there was a constraint, namely that the tangents have a fixed length of 1. Why is this constraint not just a theoretical construct? Well, what this constraint holds is, describes, is that our curve is inextensible. So like by local bending, I can't make this curve longer, right? Which physically with just writing down mathematically a function would happen. So I really have to pay attention to this constraint, which actually, as we realize, limits our theoretical prediction power, and will drive us to look into the weakly bending rod approximation. So the continuum limit was performed such that the tangent vector T of S, no vector, sorry, T of S, ds has fixed point length locally. Chain is locally inextensible. Now, interestingly, there are multiple ways I can arrive at this worm-like chain model. We here took the detour from the discrete formulation, but sort of like again, trying to connect to previous concepts. We can, in style of how we wrote down field theories, we can also argue that this is the only model by symmetry arguments. So we also arrive at this continuous chain by symmetry arguments. So we consider a curve in space. Then the arc length is describing the distance from the starting point. And I can describe now this contour by the local tangents along this curve, extending to L, and the normal vector, and also obviously R of S. And now, what is the elastic energy of a continuous space curve? From the concept of symmetry arguments. So it needs to be invariant over rotations of this entire curve. So that tells us that it can't depend on linear gradients of this curve, and it also needs to be translational invariant. So it can't have a direct dependence of the space parameterization. And so the first non-vanishing term in the gradient expansion, if we again expand like in a polynomial fashion, would then be the second order in the gradient. So the first non-vanishing term in gradient expansion is then the S squared. And just to rest assured that we're not basing that this makes sense also from the field theoretic approach, not based on symmetry argument, but actually on the relevant field theory here, namely elasticity theory. So also from classical elasticity theory, this is the energy of an elastic rod. So also follows from classical elasticity theory. And I typically derive it when I teach continuum mechanics, where spinning energy per unit length is kappa over 2 RC, R being the curvature. So now with this in mind, we can now embrace this continuum description and again derive our statistical properties. First would be the tangent, the correlation at 2 points along the arc length. This is now again performing the continuum limit of our result from Tuesday, with identifying the indices KB as the positions along the arc length. This is then minus S prime over the persistence length. And similarly, the mean square end to end distance. Which is now in this continuous description much easier to calculate because we don't have sums and geometric sums that we have to deal with, but just this integral over space. This is the whole along this entire contour. If we expand this product, we have the S prime, and then the tangent correlation, which we can plug in from above. This integral then yields the Debye function again. With the expansions, just revisiting this Debye function, that's a small d, not a p, sorry. Being defined as 2x e to minus x minus 1 plus x. Having the limiting behaviors as being an inverse function for x large and a linear expansion in x factor of 3 for x small. And so we then recover that the end-to-end distance obeys the limit of the Gaussian chain for a very flexible polymer and of a rod for a very stiff semi-flexible polymer. So that's the Gaussian chain that we cover here. And we can then again identify this Kuhn length as twice the persistence length. So twice the persistence length would be the level at which the if you have long enough of a polymer, you could consider having equally statistically independent orientations of subsequent limits again, as subsequent segments again. So it's like this idea of coarse graining the system. So R squared over L squared then decays from 1 first linearly and then in this inverse fashion. Typically, actually, in the context of semi-flexible polymer, the end-to-end distance is not the primary choice because experimentally, what is easier to assess is the radius of gyration, which in a sense is a little bit related to the, so it's a purely geometric measure, but it's a little bit related to the moment of inertia. So the radius of gyration, g squared, is defined as 1 over L 0L-DS. Looking at the end-to-end distance with respect to the center of mass of the polymer. So this is a better measure of the extent of a polymer, rather than measuring where are my two endpoints, which might statistically get close. Really to know how big is the sphere, the volume that this is enclosing the polymer. This is much better represented by the radius of gyration, which is telling me like what is the statistical distance to the center of mass of my polymer, and is particular when we consider now like polymer melts and or like entropic effects of polymers being confined within boxes or like constraining membranes. This is much more relevant statistically than how close the first and the last point of a polymer are. So the center of mass being obviously defined as the weighted center of mass. And then we can, sorry, this is square missing. Expand out, expressing both of them in terms of tension correlations again. To arrive at, again, our beloved Debye function and correction terms. And then in the two limiting cases, this tells me that for the Gaussian chain, roughly the square diameter of my mass globule scales linearly with persistence length and the total length of the polymer, but in the rod limit is really proportional to the length of the system only. Which is what. And then this prefactor of like, you know, if you think in diameters, you would expect the diameter of L/2, right? So this correction factor of 6 being due to taking the average distance of a rod with respect to its center of mass. Now we can really in single molecules measurements, we can determine this this tangent correlation, which nicely has a very simple form, namely an exponential decay, which is also something that we can very well and robustly fit, so that we can determine then as a decay length the persistence length, which is really the quantity that tells us most about the statistics of the systems. And so from single molecule measurements, of tangent correlations and measuring end-to-end distance, the so for double-stranded DNA, The persistence length is about 106 nanometers. Sorry, now it have to be an N and an M. For filamentous actin, this is 17 micrometers, and for microtubules, this is 110 micrometers to 5 millimeters as the length of the, so it's increasing stiffness, so it has a non-native dependence, sorry, that's a 5, 6, as the length of the microtubule is increasing. So you might say, oh, I don't, but you should. So why am I embedding these physiological measurements in a theoretical physics class? Because I want to teach you that it's very important in whatever you're studying in a system to know the scales of the system. Because only if you know what's the scale, you can focus your tools and questions to the relevant scales. So you need to know these ahead of time. So if I look at if I'm interested in a process that considers an entire real DNA that's encoding our entire genome, the length is way, way bigger than this persistence length. So everything considering just a pure flexible Gaussian chain model is perfectly accurate. But if I look at like a circular plasmid, which is the way of how we transfer information, how cells exchange genetic information, even the limiting is thinking of the DNA a virus is injecting into us, and I want to understand mechanical properties of these systems, then I might need to consider the semi-flexible properties. And if it's about the dynamics of cells, then everything is elastic, and we have to consider these scales. And so it's very important when you write equations and you want to describe a system and you're interested in understanding a process, to early on be aware or try to have at least an estimate. It doesn't need to be this is 17 microns, but I need to know, is it in the order of tens of microns, or is it nanometers, or is it millimeters, right? I just need to have an estimate so that I can identify my non-dimensional parameters. How big are they? Which limiting cases can I consider? What are the simulation parameters that my simulation has to run stably for, and where don't I have to care? Because in the end, what will happen very quickly is that the most limiting thing in your scientific endeavors is your time. And so you better know where you're heading early on. That said, the challenge specifically, I believe, for biological physics, but that might be true for other systems, is often enough to, like to have a number, to have a rough estimate. That can be very challenging. Just to give this away, so there's actually a web page that's called BioNumbers, which is crawling publications, and you can just search within this database to say, like, okay, I'm interested in the viscosity of the cytoplasm, and you will have at least an estimate in a system to guide your endeavors. Okay, after this detour, how about the orientational probability distribution, so that we have a little more statistical physics fun again, because also for the continuous form-like chain model, we can map this to a path integral formulation again, where the orientational probability distribution for finding a tangent vector T of L, I denote as TL at S equal L, given that T of 0 is T naught. Can be expressed by the path integral between along the contour, and here then this would be TL at L given T naught at 0, integrating, holding these values fixed, is then again having this constraint though in mind. So unfolding the same magic as we had for the Gaussian chains, where obviously this is explicitly minus kappa KBT and DTDS. That's correct. And comparing this to the path integral for the Gaussian chain, we realize we are back to solving diffusion equations. Here, the diffusion equation is in L. So sorry, no, this has to be as a function of S. I'm sorry, T. TS S having started at T naught at 0, where the diffusion equation, we have D being KBT over 2 kappa. Now, and just to be consistent with the initial condition, being that obviously if we start at 0, this is a delta. Now, what is different with this distribution equation yet is this, as I already advertised, annoying constraint that our curve is inextensible. And what does this mean now in the context of this diffusion equation? Well, it means that we're actually looking at the diffusion of the tangents on the unit sphere. So, which basically constrains this Laplacian that we have here. So, to satisfy the constraint that T of S squared, well, it's actually is 1. Diffusion is on a unit sphere only, which means that this Laplacian acting on a function that's a function of the coordinates, the spherical coordinates. Plus 1 sine squared theta d squared z d phi squared. So that's the Laplacian on a unit sphere. which you have seen before. Again, there's a limited amount of equations we can solve. Diffusion equation is luckily one of them. In particular, this one you solved is looking at the momentum operator in quantum mechanics. So this is actually analogous to the angular momentum operator in quantum mechanics. And so we know the solution. The solution is an expansion in spherical harmonics. So G with now denoting this tangent position by an omega, which denotes the final states of these both of these angles that I need to specify. And similarly, I take a small omega to specify the initial both of the initial angles. And then we know the solution as being of this form that we're familiar from quantum mechanics plus L with YLM of the initial omega being the spherical harmonics. You know, that's the solution to the Green's function. That's the Green's function of the diffusion equation with initial condition given above. And so this, just to look back to what we just derived, this offers another way to derive statistical properties, namely the tangent-tangent correlations, which here would then be what's the average of the angle enclosed, which we can then with this Green's function write as the integral over all angles, and its propagator. It's particularly easy in this case because what we can do is we can identify that what we have here, the cos theta, is related to the spherical harmonic of L equal 1 and M equal 0, which is given by a half 3 over pi cos theta. So I can write this term as a spherical harmonic, and then I can use the orthonormality of the spherical harmonics to solve the tangent-tangent correlation. So we spell this out, just copying down the Green's function from above. L plus 1 is summing over M minus L to L y L M omega y L M of 0, and then writing this as 1 0 of omega and normalizing it by the 0 state. Sorry, 1 0, just to take care of the prefactors. Sorry, in the 0 state, the omega I denoted with the 0. Then we know that these sums, because of the orthonormality, give us a delta L1 and a delta M0. Sorry, that went too far. this one. And then if we enter L equal 1 in here, doesn't matter, then we get a factor of 2. And so that's minus D 2L S minus S prime that we get here. Oh, sorry, there's a sorry, that was not S and S primes, and then I have a S minus S prime here. So there we go. So, and then this is exactly the same as before. Remember, we have the here. The diffusion constant was kBt over 2 kappa, which is 1 over 2 LP. And so, so I don't know why there's an L left. Put in the L. There we go. So it's distance over LP. And similarly, the end-to-end distance vector would be we find, well, directly, I don't have to do this again, sorry. So generally speaking, we can basically unfold the full power of the Green's function here, but really the challenge is that we have the stupid inextensibility constraint that makes it hard to calculate more characteristics than the ones that we did. So generally speaking, the constraint of index 10 stability makes it then basically tangent correlations and things that are just related to tangent correlations, namely end-to-end distances. Moments. Therefore, we need approximative. Right. And in this realm, I would like to introduce you to the concept of the weakly bending rod approximation, which has proven very powerful. So the weakly bending rod and it's really like I believe like seeing a lot of like different strategies of how you can approximate problems. That's very powerful, because that's typically where the challenge for the researcher lies. I'm like, hey, I can't solve the problem. Surprise, this is always what happens. What can I do? So the idea is that if I look at a semi-flexible polymer, then it will be wiggling in space, right? But in the end, you know, it's probably more or less stretched out, right? Because that's like, you know, if the length of the polymer is smaller than the persistence length, it's more or less a rod. And if we relax this a little more, this constraint, you know, it should still be more or less stretched out. And so what I can now do is to say, if I go along this contour that's extending from S equals 0 to S equal L, how about I just project my my polymer along, well, actually, sorry, that was stupid. doesn't need to be defined in space, could also be so like this. My things make easier. So how about projected along a curve through the middle? And then what I would have is I would describe now any point as perpendicular undulation in space. That is a two-dimensional vector because I have two. And then I have another measure of namely of how far along am I along my polymer, and this is given by more or less the arc length that is extending along here, right? This is my arc length, but this is not really my arc length. There is a small correction that I have to take into account, namely our polymer, our parallel, which also depends on S, and that's the so-called stored length. So for an elastic rod, the stored length would be like a rod, just a rod, rigid rod. The stored length would be 0 at any point, and the undulation would also be 0. So we have two parameters that are small in that limit, and now we can sort of expand in these terms, these two quantities being small. So an almost fully stretched chain, small deformations from the stretched duration, and then be written as which would be like in principle the curve would be a curve in X, Y, and Z, and now I project it onto our perpendicular, which is a 2D vector, and S minus R parallel of S, the stored length. If this parameterizes my curve, then my tangent vector I can calculate as just a derivative. So that would mean that I have the perpendicular ds over here, and here I have a 1 minus the r parallel ds down here. Sorry, that's a vector. Now remember, the tricky thing was the inextensibility constraint. So inextensibility requires that the locally the absolute value of the tangent is equal to 1. So if we now calculate this, that says that we have dr ds squared plus 1 minus dr parallel ds squared. This should be equal to 1. Allow me to expand the second term as 1 minus 2 dr parallel ds plus dr parallel ds squared. As we said, like the in the limit of a rigid rod, particularly the stored length is very small. Also the undulations, but also if I deviate from that limit, I could I can assume that this stored length is small. So if we neglect higher order terms, so we say this is small or small deviations from the rigid rod, then and let me actually copy down this one here. We can, in this approximation, relate the spatial derivative of the stored length to the undulations and find that the spatial the arc length derivative of the stored length is roughly a half of the squared, which again satisfies that we approximated this term to be the smallest among all three considered, because it says that this term would be fourth order in the undulations, right? Or twice the order of this term. And so we see that the length fluctuations are of second order. Oh no. In bending undulations. And so when we then go back and calculate the Hamiltonian, which is the spatial derivative of the tangents, right? We can put both terms together again. Let's try. In bending undulations. So, okay. Not okay. And then the next goal with that in hand is that we all of a sudden then can calculate force extension curves again. Remember, I showed you the data of the force extension curve of the DNA, which nicely captured both the Gaussian chain limit and the inextensibility for large forces, and the flexible polymer modulus were really able to capture qualitatively the dynamics, but really on a quantitative level there was a distinct offset, even for DNA. And so the hope is now that if we calculate, again, the force extension in the context of semi-flexible polymers, we'll be able to capture this deviation that we observed in this data. And we need the weakly bending rod approximation to do so because of this stupid inextensibility constraint that is sadly essentially capturing the physics of, you know, molecules being bound to each other and therefore inextensible. And so it needs to be taken into account. And here the weakly bending rod approximation allows us to do so. So now we neglect our parallel contribution to the Hamiltonian. And the so-called weakly bending rod Hamiltonian becomes kappa over 2 over 0 ds, and then here we have a dr undulation second order derivative term. So we only have to account for the undulations. And then we can turn to the mean square transverse fluctuations to quantify them and use this to calculate the force extension relation. So we're interested in the end-to-end distance in parallel that we had before for the Gaussian chain as well. And now in the context of the weakly bending rod approximation, this is, right, this extends, as we said here, is integrating over the tangents along this direction. The tangents are 1 minus r parallel ds, so I just have to integrate over those. So that's 1 minus d ds of r parallel of s, which with this relationship I can write in terms of the undulations. The first integral I solve, it gives us an L, and then we have a minus. That's the length that's stored in the undulations, the half from the scaling, the S, and then here we have the transverse fluctuations squared. Now we can apply force F at both ends. Chain. And then the weakly bending rod with force is just, again, the square undulations. And then minus F acting on the parallel direction. And if we spell this out, just copying down the first term, we get squared squared plus F over 2 0 L ds of now a linear first order derivative squared. It's this term. Well, our mixed constants that are not changing the dynamics. And now we can solve the statistics of the systems, but we have to specify the boundary conditions. And so our boundary condition would be so-called clamped ends, which says that there are no undulations at both ends that I'm applying the force to. So that would be that both the positions, the undulations are 0, as well as the derivatives. And then I can make the ansatz to expand these undulations in a Fourier series. These are the two independent transverse modes. And that's the normalization factor. And the case as chosen as, sorry, to match the boundary conditions as n pi over L. And yeah, so the normalization factor comes from if I integrate 2 over L sine ks 2 over L sine k prime s, this then gives me a delta del k prime. And now if we plug this into our weakly bending rod approximation above, then the Hamiltonian in Fourier expansion reads, we have a half with sum over k, because we have a product, we have two indices, I, and so because of the normalization, we end up with here second order derivatives gives me a k squared kappa, and the second term we have a prefect of f, and we have a linear derivative. Sorry, k. This gives me a k squared, but there's another square, so this should be to the power 4. And this gives me a k, and then this is squared subsequently, so that gives me a plus fk squared and aki squared. There we go. Now we from this relationship can assess the magnitude of the individual modes that is given by these expansion terms A, because we know from the equipartition theory that each transverse mode will have an energy of a half kBt. This is what can be thermally excited, and so this allows us now the equipartitioning theorem states to determine these AKI, at least statistically, states that every transverse mode will have an energy of kBt. And so if we plug this on the left-hand side, we see that AKI squared is kBt, the halves cancel, k to the 4 kappa plus fk squared. And now we can put this back in our Fourier expansion to calculate the square of the undulations in real space, and then end in real space. We have, sorry, squared was, this is for now at f equals 0. We would have 2 over L, the normalization factor, sum over k's, each being kBt over k to the 4 kappa. Let me rearrange terms to realize that what we have here is 2 kBt over kappa. Noting that these k's due to the boundary conditions are n pi, is it over L to the power 4, obviously. We can have an L cancel, so then this becomes a sum over the L n's. There's an L to 3 left, and we have here n to the 4 by 4. And you don't need to know, but these sums again tabulated. So the sum over n over to infinity of 1 over n to the power of p, sorry. Actually it has a name. It's called the Riemann zeta function. And you can calculate its values, notably z for and p equal 2 is pi to the power of 2 over 6, and zeta of 4 is pi over 4 over 40. Oh, 40? 90, I think 90, sorry. Which is the case that we have here, right? So if we plug this in, we see that this is 1 over 45. Let me identify. This is 1 over the persistence length. The pi's cancel out, and we're left with L to the 3 over LP. So that tells us that the width of the undulations grows with the length of the polymer to the power of 3, but also increases the stiffer the polymer becomes. So the width of undulations, so the amplitude in a sense decreases. Sorry, the square, obviously, right? With persistence length LP and increases with polymer length. And again, notably, we could have found actually the same scaling relationship directly from the Hamiltonian. So we, all like knowing about zeta functions and digging them up wasn't necessary to have just this scaling relationship. So can also find the scaling directly from the Hamiltonian. Because in the end, what we were comparing was like, what's the thermal noise that we put, the thermal energy that we put in the system, it's KBT, and it's put into these undulations. And so in thermal equilibrium, there should be the same. So KBT needs to be of the order of the energy, and without like going to all Fourier space, we know here, wait, there. So force 0. So we have here kappa over 2. This scales with the length of the system, so kappa over 2 times L. And here we have a derivative of the undulations with the spatial dimension. The spatial dimension that we have is again the length. So we have undulations squared over length squared to the power of 2. So if you just put down just the dimensions of the system, so we had kappa over half from the integration in L, and then we had these undulations squared and an L squared here to the undulations second order of, there we go, and then this says if we rearrange terms that are squared should be proportional to L cubed over LP. Scaling comes out. It's only the prefactor that we need to math for. Notably, what this teaches us that we can have this scaling relationship directly from the Hamiltonian, that this actually is independent of the choice of the boundary condition that we made. So scaling is independent of boundary condition. Only the prefactors depend on it. Okay, so this was just talking about, again, the magic of scaling relationships in this context, but as advertised, we wanted to go for the force extension relationship. So if we now look at the end-to-end distance under force, so we're interested in this R parallel as a function of the force. Remember that was the length minus the stored length in the undulations. So that was ds squared. sorry, and now statistically speaking, sorry, I want to take the I want to have these some thermal statistics. And so what we can plug in here is now this relationship, putting in the AKIs here. So because it's a derivative, we get a factor of k again. So this is minus, there's a half, and then we have sums over k and I. The k, and we're squaring it, gives a k squared. And then we're putting in the relationship for the, it is, for the amplitudes of our Fourier expansion, so the kbt over, and so on, kbt over kappa k to the 4 plus f k to the 2, which we can reorganize a little bit by noting that these simplify, and now you see why I gave you the zeta function as a function of 2 and not only of 4, because now this becomes L minus sum over k. The i's goes over the two transverse directions. Since the amplitude don't depend on the transverse direction, this gives us a factor of 2, which cancels, this sum cancels with that 2. And we're left with kbt kappa k squared over f. It's still too complicated. We don't have a tabulated function for this sum, but if we expand for small forces, we get that this is L minus kbt, and then this term becomes more easier to handle, so we get a 1 over k squared minus f over k to the 4 plus higher order term. Remember again that kappa is LP kbt. And then this allows us to make kbt over kappa into LPs. Let me rearrange terms and pulling out an L. So we get this nice L over LP over L, like dimensionless factor in here. The first sum, that's this zeta function up here. So we get a 1/6. And the second term is the 90 popping up, 1/90th. Here now L over LP squared. And the other non-dimensional factor is then FL, balancing the thermal energy and higher terms in F. Okay, so what does it mean? So here we really now truly discovered physical behavior that we haven't seen before. So now the weakly bending, in the weakly bending rod approximation, we have two opposite terms popping up, right? So the end-to-end distance is given by the length, that's the one, but then there's a term that has a minus sign to make the end-to-end distance shorter, and there's a term that has a plus sign that makes it longer. Obviously small forces don't take this positive term too seriously, because obviously it can't, the end-to-end distance can be longer than the total length of the polymer, but it tells us about the meaning. So this is the extension we get by the applied force, and this negative term is the thermal contractions due to the bending on relations. Thermal contraction due to bending undulations. And so if we now compare this result to the entropic spring picture, the Gaussian chain, there we have our parallel of F being LB over 3 kBT F, which we can map to this system by remembering that here the Kuhn length is 2LP. So what we actually state above should be compared to FL KBT, and then the is a 2/3 LP term that's popping up, or like if I make it so it grows linearly in the persistence length as before. Okay, so these are the results, and now indeed this force extension relationship nicely captures our DNA data. What is really instructional is that now this also allows me, like these simple relationships. I know the persistence length, I know how long my polymer of choice is, so I can estimate really what kind of forces are actually required, like which kind of forces are actually making a difference in the systems or not. And so this brings me to talk about typical numbers of biopolymers again, just so we know roughly a scale. So as a number that is really useful to memorize, the scale of thermal energy at body temperature is 4 piconewton nanometer. So kBT is 4 piconewton nanometer. That's the scale, roughly. That's the number. And so this is the thermal contractions that we put in. And now, like DNA, we can consider as an entropic spring, because the persistence length is around 50 nanometer for, maybe the Kuhn length with 100 something. Then the force that would be required to stretch, well, let me just rearrange this quickly, 3 kBT to LP R parallel over L. So the force to stretch, say, a DNA of 10 microns by 10%, so to 11 microns, if we plug in these numbers, this would be 0.1 piconewtons times L. So say L is 10 microns. We need F just 10, a tenth of the piconewtons to stretch DNA to a length of, so these are really tiny forces, but it looks very different if we're talking about the cytoskeleton, which is a semi-flexible polymer where the persistence length was 17 microns. And here we obviously have to go to the Warm-like chain model to relate how much can we change. The distance, end-to-end distance, is then related to this positive term, which scaled with this being squared L over, KBT. times the force. So if we plug in the persistence length here, again, we want to have a change of 1 micron, and we consider a total length of 10 microns. We here need a force of 0.15 piconewton in order of magnitude larger. And finally, we right now just explored the limit of small forces, but actually in this general description that we had, here, this we can also look in the context of the strong stretching limit. So if we have large forces, so in the strong stretching limit, and I'm now just looking at the change, so I'm omitting this L. So our formula was we're summing over the K's, that was KBT over kappa K squared plus F. Now, to explore the limit of F large, I note that actually the modes that I'm expanding on, they were N pi over L. So the distance between individual modes, this is just N over L. And so I can actually also take for F large this to a continuum limit. Let me just pull out where my sum over K's comes in integral dk L pi 1 over kappa K squared plus F, that can be solved to pi squared over 4 kappa F, which we can briefly rearrange to be L KBT for F LP. So just to write down this extension curve would be then L1 minus a half KBT FLP. And so just to have an overview, taking both limits together, we see we have this entropic effect, and then this force effect that I'm writing here in a different, yet another form. Because this FC that I use here as a reference limit is, again, as I said, like you should always take, like saying force is large or force is small is not an accurate statement. You should always send a non-dimensional number to 0 or to big numbers. And so here actually the reference force is the so-called Euler-Buckling force. So if you take a rod and you compress it on both ends, this won't happen with my pen, but you know, there's a specific force where eventually any rod will buckle. It's a very large force for my pen, but it's a smaller force for like something more flexible. And so that's the an adequate choice of a non-dimensional number. And so this is pi squared, which you can force. And so indeed, if we now look at the results of the force extension curves, we indeed see that here we have in green the weakly the worm-like chain interpolated, that's the weakly bending rod approximation, and in blue there's an exact result and nicely captures the dynamics of the DNA. So in comparison to experimental data, we find the force extension to be linear for small forces and quadratic for large forces. And there are deviations due to thermal undulations at very small forces. Okay, so this is concluding the journey into semi-flexible polymers. I will give a short outlook into polymer dynamics, just to advertise again that for me, advanced statistical physics is only half of the fun of statistical physics, because the real challenge is non-equilibrium physics, at least nowadays. And so just to advertise that it would be fun to look into the stochastic processes class that Uli Gerland is teaching next semester. But that's it for now. Thank you. Stop. There we go.